Hi, I'm Professor Frank Fronczak. I'm a professor in mechanical and biomedical engineering departments, and I'm here today to talk to you a little bit about the overall design process. Recognize that I'm going to try to keep this brief, try to do it in 10 or 15 minutes or so, but recognize that it's a topic that really is involved and it covers a lot of material. So I have to be very brief and give you an overview of the thing rather than going into much detail. Now, the design process, as the name implies, is in fact a process. It flows. That is, there's a starting point, follow-up points, first, second, third, and fourth points, and so on that you do, or activities that you do. The first stage of the design process, and if you look at the accompanying slides that accompany this video, you'll see that there are, this process starts with problem identification. It flows from problem identification into concept generation and evaluation, from concept generation and evaluation into embodiment or detailed design, to design validation. At that point, we're pretty much finished with the design process, but then the product realization process continues on with production of the product and then implementation of the product going out into the market or being used by the client or the customer. So now we'll go through the process, the steps of the process. As I said, the first step is problem identification. This is crucial. You have to know what problem you're working on. Make sure you understand the problem thoroughly. This will typically start off by you communicating with the client or whoever it is that this design is being done for and understand what their needs are. Those needs may be real and perceived needs. They may be able to articulate needs in very general terms to you, like saying, I want something to do something faster. They may not be able to articulate specifically what they want. There are also, as I said, perceived needs. That is, they will be able to tell you what they think they want, but there may be something that you rely on your own experience, your own judgment to say, hey, they also need this, even though they're not articulating that. So the first step, like I said, is to come up with this problem statement, which is a concise statement of the needs as you understand them. It also serves as feedback so that you can tell the client or the customer, this is what you think their needs are, this is what you're trying to do, this is the problem that you're working on. So they then come back and say, yeah, that's what I wanted, or no, you missed the point, so it serves as this communication tool back and forth. Once you have the general problem statement, this identification of the problem needs, what you have to do is convert that into a specification. That is, you have to be more specific. We convert the general needs, for example, I want this thing to go fast, into how fast? Well, maybe it has to be accomplished, a process has to be accomplished in 20 seconds. Furthermore, you break it down and say, well, 5 seconds of that 20 seconds will be allocated towards preparation. 20 or 10 seconds of that 20 seconds will be the process implementation itself, and then 5 seconds at the tail end will be for validation of it. So the product design specification is crucial in converting these general statement needs into engineering specific things. Right? It's a detailed transformation involving all the different aspects of the design. Those aspects of the design include things like manufacturability, size, strength, what size package it has to be fit into, what's the shelf life, and so on. So you come up with these design specifications. You have to make sure you do a good job on that because that guides the rest of the process. If you don't do a good job in this design specification, you're going to run into problems later on. Right. So once we've got the problem identified, the next step is to go into concept generation. What we're trying to do with concept generation is generate multiple potential solutions to the problem that has been identified. Now, like a story that I like to tell is, if all you have in your toolbox is a hammer, everything looks like a nail. Well, if all you have is one design, it will look good to you. All right, so what you really want to do is make sure you generate lots and lots of concepts. By lots of concepts, multiple concepts, I mean 100 or so. Now, this may seem like a daunting task. Geez, we had a hard time coming up with the first idea. How are we going to come up with 100 ideas, 100 different ways of doing this? Well, there's some techniques that you can use that will enable you to come up with lots of ideas. One of the ideas or one of the techniques that's used, that's once again referred to in the some of the references that are at the end of the slides over here, is functional decomposition. You start looking at things in terms of abstractions rather than in concrete terms. So we start looking at things such as energy transformations, looking at material transformations. We look at information transformation. For example, let's look at a real simple example of a toaster. We have energy transformation in the toaster. We're converting electrical energy into thermal energy through the resistance of the wires. We also have a material transformation. The bread is transformed into toast. That involves an actual transformation of the material, a chemical transformation. There's also information transformation. So what information? Well, there's on-off. You either turn it on, you turn it off. The information, when the toast is done, it pops up. That is transferring energy or transforming information that the process is done. The toast pops out of the toaster. So if we look at things in abstractions, it generally enables us to come up with lots of solutions, whereas if we look at things in concrete terms, very often we're limited more in our ability to come up with concepts. Now, there are also some other techniques that are used that have been proven to be very useful. One of which probably you've heard of is brainstorming. Now, brainstorming has gotten a bad rap over the years because it has been misused very often. All right. On the other hand, if you use brainstorming using the rules, and there are rules, and once again, these rules are outlined in some of those books that I've given at the end of this slides over here. If you follow the rules, you'll generally find that good brainstorming session, well conducted, will generate on the order of 100 solutions in about an hour and a half of time. There are some specific techniques that if you get stuck, for example, using Osborne's checklist, which enables you to take the brainstorming rules and when you get stuck, to go through the checklist and start coming up with stimuli to your creativity, which will enable you to generate more solutions. Another technique that's not widely used, but which I find to be particularly useful, is the use of a morphological chart. In this case, you break up the problem into multiple individual functions, and then you find solutions to these individual functions. It's much easier to solve lots of simple problems than one complex problem. Then you take these multiple solutions to these individual problems that you've come up with, and you can combine them. And when I've done this in my classes, we'll have, in a 15 or 20-minute session, we will generally generate easily 100 to 200 different concepts. All right, so now we've got our concepts generated. What do we do with these concepts? Well, once we have these concepts, we can't explore all these concepts in detail. We don't have enough time, enough resources to do that. So what we have to do is evaluate these concepts. And we have to go out and pick the one or two that look like they will have the most likelihood of satisfying our design specification, our design objectives. Right? So how do we go about getting rid of the chaff and getting to the real good ones? Well, the first thing we do is we do a quick feasibility study. That is this thing at all reasonable? Maybe we came up with a concept during our concept generation stage that involved coating some device in platinum or some precious metal, and we realized, no, that won't meet our criteria for total cost of the product. It's going to be unfeasible because it's too expensive. Or it doesn't meet some of the other criteria. It's just not feasible to do. So we get rid of a whole bunch of those. And what you'll find out of 100 or so, you'll typically be able to get rid of 70 or 80 or maybe even 90 of the solutions as being unfeasible. Another technique that's used is just listing the pros and cons of these different devices. I mention this not as an endorsement of this technique because, in fact, it's a lousy technique. It's a very immature technique. It's not sophisticated enough to really provide very much meaningful results because it doesn't have any idea of the importance of the different relative pros and cons. So while you can do it, and it may be useful in identifying what the issues are, it shouldn't be used as a decision tool to help you decide which of these concepts to use and which not to use. Like I said, I mention it because it's so ubiquitous and people tend to use it, but it's a very low-level decision-making tool. A much more sophisticated, at the opposite end of the spectrum, is a formal optimization, which I won't spend too much time on because it's typically beyond the scope of the projects, of the kind of projects that most people are working on. But if you have a very, very straightforward process with a lot of detail that's available to you, a lot of information that's available to you, you should recognize that there are formal optimization techniques that you can use. A more useful technique that I found is what's called a controlled convergence chart. And once again, more information on this will be found in the references at the end of the slides. The controlled convergence chart allows you to compare side by side the different options that you have using the criteria that you established in the design specification. Remember how I said the design specification is extremely important. If you don't do a good job on that, you're not going to be able to do a good job in the subsequent steps. What you do is you take the criteria that you've established in the design specification and you compare each of your 10 or so options that you have, compare them to each other using the criteria that you established in your design specification. It's a very effective technique. It can be done quickly. A group collectively together working on this can get through their 10 concepts with their design specifications in an hour or 2 hours and come up with 1 or 2 designs that the group consensus is, hey, this is probably going to be the best design, the best option for us to pursue over the rest of the time that we have to work on it. So now, once we have our concept, 1 or 2 concepts that we're going to work on, we have to recognize that's just a concept. That doesn't have the detail. We now have to get into the detailed design or the embodiment design. We have to flesh out the skeletal structure that we have in this concept. And the concept only goes so far. It's a concept. It's like a good idea. You know, good ideas are a dime a dozen. We have to convert that good idea. We have to put details, the size, we have to get the material selection correct. We have to get all of the details correctly before we have a successful product. There's 2 expressions: God is in the details, the devil is in the details. Those seemingly contradictory statements are both true. A design, in order for it to be successful, in order to have goodness, to have that essence of goodness over here, when we talk about God is in the details, we have to have the details paid attention to. We also say the devil is in the detail, because if it doesn't work, it's probably because not the concept was poor, but because the details were not taken care of carefully, okay? There's some little screw that just keeps on breaking, or some little part that keeps on breaking because it wasn't detailed correctly. Also, the devil is in the details because it takes a tremendous amount of work to do it right. So, working out the details. How do we do this? Well, we have a lot of design tools. We look at it and we identify the different things, the different aspects of the design that we have to pay attention to. For example, safety, manufacturability, assemblability, the environmental issues. How much energy does it consume? What's going to happen to it when it's disposed of? Does it produce any toxic waste during the production process or during the use of it? Effective material usage. Is it strong enough? Is it stiff enough? Is it made out of the right material? Should it be aluminum? Should it be steel? Should it be plastic? Should it be wood? Should it be a natural fiber? All these issues have to be worked out. Ergonomics, the interaction between the tool and the device. So we look at all of these details, we work about them. One thing to keep in mind, don't focus just on one detail. If you focus on one detail, forgetting about the others and say, well, I'll do these things in sequence, what you'll come up with something that perhaps is very safe, but it's not economic or it can't be manufactured. So you have to be focusing on all of these aspects simultaneously. That's a real tough thing to do. All right? It's not like your classroom problem courses where you have a body of material and say, oh, we just follow the sequence, we're focusing on this aspect. You have to not only tie in everything you know, you have to tie in things that you don't know yet. You have to study about, okay? All right, so once we've got our details worked out, and while we're working out these details, we have to do a process or step called design validation. At some point, we're going to want to look at this and say, will it work the way we think it will work? Will it work the way we plan it to work? All right? Part of this design validation involves analysis done during the detailed design. But a lot of the design validation can't be done until we have a design already developed in sufficient detail to do an analysis. Now, what we're doing is there's two methods or 2 approaches for doing design validation. One of which is analysis. You use the analytical tools that you've been taught, classical analytical tools, for example, in strength of materials, you learn sigma is equal to MC over I, delta, the deflection, is equal to PL cubed over 48 EI. So you have these analytical tools that you can use in order to relatively accurately predict whether this thing will do what you want it to do. But a lot of problems defy the classical techniques, the simplistic methods, so you have to go to more sophisticated computational techniques. This is where you do things like finite element analysis, computational fluid dynamics, simulations using MATLAB or Simulink or some other simulation package to do kinematic and dynamic simulations. So you look at your design, you try to determine using analysis, whether it's classical or computational techniques, in order to predict whether this thing will do what you want it to do. Now that's good as far as it goes, but we also need physical testing in order to really make sure that this thing will work. It's, unless it's the simplest design at all, there's going to be some physical testing that will be involved during this design phase. What it may involve is just a mock-up. You may look at it, a mock-up is just a non-functioning device that gives you the spatial relationship between the different elements to see how does it look. Is it big enough? Is it small enough? Will it fit? Where should the instrumentation be, and so on. That's what mock-ups do. We also have proof of concept devices. That is, there may be one aspect of the overall design that we're not sure how well it will work. We've got a concept, our analysis predicts it will work, but we don't have confidence in our analysis because the complexity of the device is beyond what we're confident of in terms of the analysis level that we can do. So we build a proof of concept device, which is a functioning portion of the overall device. And then finally, we build a prototype. That is, we build the device in its final form, or what we think will be the final form, and we test that in a condition that we think that it will actually be used in. And we find out, did we capture everything that we should have? We may find that it functions correctly, but it operates too noisily, so we have to go back and address that issue. All right, now I laid out this design process as a nice flow where we go from problem identification, which involves a problem statement and a design specification. The next step was concept generation and concept evaluation. Then we went into design embodiment or detailed design, and then we went into design validation. In fact, the process is much messier. Okay, you're going to find that you're going to get into the detailed design and you're going to find out, wait a second, there's something back at the very beginning that I didn't understand or I misunderstood, or I need some more information from the customer. So you have to loop back to that initial step. Or you may have had a design specification that you find out, wait, this is unmanageable. Or you get some information late in the process that says, oh no, we thought that we would be able to ship this thing by UPS if it was a certain size, but that's beyond the size that UPS allows, so we have to go back and change some of the design details that we thought. So in fact, the process involves a lot of iteration. It involves going back and looping back. It involves flexibility. Now, what does it take to be a good designer? Okay, well, it takes a couple things. First of all, it takes knowledge. You have to have an understanding of the concepts, the math, the engineering, the technology that you're dealing with. But knowledge is readily, straightforwardly acquirable. That is, a teacher teaches you something, you learn it, or you read it in a book, or you see it done, you've got knowledge. Knowledge is simple. Okay, but you have to be able to use that knowledge, okay, and that requires skill. So we have knowledge. That skill enables us to use that knowledge effectively. We can know how to throw a curveball, but we are not necessarily able to throw a curveball because we don't have the skill. Skills in design are like skills in other things. They require practice, they experience. So you develop these skills with time, all right? But also, just as importantly, is attitude. So you have to have knowledge, skill, but you have to have the attitude. If you go into it without the right attitude, you're not typically going to be a successful designer. By attitude, you have to have the attitude of an explorer. You have to go and say, look, here's something that we're going to go and try to figure out how to do it. Nobody has done this before, so we're going to go out there and we're going to explore new territory. Now that involves risk-taking. You're going to have to be come to grips with the fact that you may follow a certain path, you may do an awful lot of work, and it may be a dead end. It's a blind box canyon, you can't get out, you have to back up. So you have to have this ability to take risk, you have to have the attitude where you will accept risk-taking, and then when you fail, you have to have the attitude to say, well, okay, we're going to try a different route. Trying this different route is one reason why we go through these multiple concepts over here, because if we find out that the one concept that graded out highest didn't work, we at least have a fallback position. Okay, finally, once again, I tried to cut this down to as short a period of time as I could. What I would suggest that you do if you're interested in this topic, look at some of the references. There's thousands of books on this. I only selected a very small few that I think you might find particularly useful. In any case, good luck on your design projects.